Okay. Thank you very much. Can everyone hear me?
Yes, I can hear you and
see
you.
Yeah. Can you see me too?
Yes.
Okay. Good. All right. So today I want to talk to you about this pretty peculiar comet that we've been following for the last few months here. So this kind of, very brief introduction. I mean, Maria and Diana have already done an excellent job of this, but just to reiterate that cometary composition is very primitive, and because of this, we think that we can use knowledge of cometary composition to understand the chemistry occurring in the early solar system. And the second thing I put on this slide is just a quote that's often ascribed to David Levy, a famous comet discoverer. He says that comets are like cats. They have tails and they do precisely what they want. And I just kind of want you to keep that quote in mind, because I think this comet I'm going to talk about really encapsulates that sentiment. All right, so this is a comet called C2016-R2 PANSTARRS, an alphabet soup. So discovered in September of 2016 by the PANSTARRS survey, a perihelion pretty far away from the sun at about 2.6 AU. I don't know why is the slide.
Oh, you might not have the cursor.
By clicking the arrows to the bottom left.
Okay. I get this on my display, like it started, my slide started moving on me. But anyway, yeah, so perihelion pretty far from the sun, 2.6 AU. It's reaching it in actually a few weeks. Pretty long orbital period of 20,000 years. Pretty faint magnitude as far as comets that we typically target spectroscopically go, of 10 to 11. So really, all these things together, this is not, on its surface, you would not really note this as a particularly noteworthy comet. However, this past November, we took some imaging of it. So here is an image that we obtained from McDonald Observatory this past November. And this is in a filter called the CN filter. So this is designed to isolate emission from the CN radical in cometary coma. And basically, and usually comets here, to first order, will look more or less symmetric. But you can clearly see that there's a strong tail in this image. So this was very odd, and we had never seen this before. And the best we could figure is that this was an ion tail that was contaminating the filter flux at these particular wavelengths. So we did some spectroscopic follow-up in the optical and saw a very unusual spectrum. So usually in the optical, cometary spectra are dominated by emission lines from radical species such as CN or C2 neutral molecules, whereas these molecules were pretty much absent from this spectrum and instead dominated by emission from ions, mostly from CO+. So you can see one of the main bands here of the CO+, and there were several bands throughout the spectrum that we were able to observe. And what was particularly noteworthy is that we were also able to detect N2+ emission, which is extremely rare to see in comets. And this is the first time I'd ever seen at such high spectral resolution, shown here. So I don't want to spend too much time talking about the N2, because obviously we're talking about carbon here. But I did just kind of want to note that this comet has about nearly the highest N2 to CO ratio of any comet where this ratio is available. And we talk a lot about this detection in a APJ letter that Anita Cochran and I put out a few months ago. So really kind of the main point here is that combined from these imaging and spectra that we took, we really could see that this was a very interesting comet, a very, very unique, maybe even unique comet. So we alerted the cometary community to try to get as many observations as possible, and a lot of people have followed up. So a lot of people were able to get observations in the submillimeter, Maria Womack included, and were able to confirm the very high CO abundance in this comet. So I'm going to talk a little bit more about some infrared follow-up that we were able to do. So first, we were able to obtain some time on the new iShell instrument on NASA IRTF to look for CO and other parent volatiles in the infrared. So in the top panel here, you can see that we were very easily able to detect CO, again confirming the very high CO abundance in this particular comet. So here you can see 9 lines of CO that we were able to detect. And then we were also able to detect methane, weaker, but still clearly detected. You can see the R0 line here. We also were able to obtain time on the Spectra Space Telescope to look for CO2. So Maria alluded to this a little bit in her talk. But basically what we're able to do, let's back up. So for carbon dioxide, that we cannot study that from the ground due to severe telluric absorption by telluric CO2 in our own atmosphere. So we need to go to space in order to do that, and Spitzer is perfect for that. So right now, it only operates in a warm phase, so it's operating images at 2 wavelengths, one at 3.6 microns and one at 4.5 microns. So the 3.6 micron is more or less just dust continuum. There's not really any strong emission features in that band, whereas at the 4.5 micron band, you get dust continuum, but you also get emission from CO2 and CO. So these are images that we obtained from Spitzer of C2016 R2 PANSTARRS. You can see that it's really faint in the 3.6 micron feature and much brighter in the 4.5 micron filter or bandpass. And this is a clear signature that there's an excess of gas emission that we are detecting. Now, the tricky thing, as Maria mentioned, is to disentangle whether you're seeing carbon dioxide or CO, because both are present in this bandpass. However, for this comet, we plan to have near simultaneous CO observations, so we can know what the CO is and subtract it off of these images to then isolate the CO2 contribution. All right, so here's a table that probably has too many numbers, but basically here's just a table of a bunch of different carbon-bearing molecules in this comet, and also N2 included for completeness, with mixing ratios compared to water and to CO, and also comparison to the average values of mixing ratios compared to water and CO for the sample of comets observed to date. And I'm not going to go into detail about the specific numbers here, but really the main thing to note is all the green numbers compared to water, which indicates a large enrichment compared to water, and all the red numbers in the CO column, which indicates heavy depletions compared to CO, compared to other comets that we have observed. And these are quite strong depletions, by at least an order of magnitude to even 2 orders of magnitude in some cases. All right, so again, a lot of numbers, maybe don't kind of drive this, to try to drive this home, I kind of put this more in a chart form. So on the top is our quote-unquote average comet. So as Maria talked about in her talk, that, dominated by water, and then you have CO2 and CO as the other dominant volatiles, and then you would have methane and N2 as, trace volatiles. Whereas you can see here in the bottom, this is that same chart for R2 PANSTARRS. And you can see here that CO is by far the dominant volatile, followed by CO2, and then water is actually almost relegated to a trace species in this particular comet, actually comparable to N2 even. All right, so what does all this actually mean? So one thing to note is that this comet was at about 3 AU from the sun when we observed it. As Maria mentioned, at 3 AU, water is not fully activated for sublimation. So some of the elevation of mixing ratios compared to water can be due to that. So you could but you can explain that about a factor of few due to the large heliocentric distance, but not the 2 orders of magnitude that we're observing. And additionally, mixing ratios such as methane over CO and CO2 over CO should not be affected at 3 AU. Those are well within the sublimation lines for both of those species. So even the depletions compared to CO there cannot be explained in that fashion. So another thing to kind of note, that CO and N2, which are among the most dominant volatiles that we are able to detect in this particular comet, are the most primitive molecular forms of carbon and nitrogen in the universe, which could be suggesting that wherever R2 PANSTARRS formed, that there really wasn't a lot of chemical processing going on. There wasn't any processing that was converting the CO and N2 into more complicated molecules. CO and N2 are also extremely volatile, meaning that this comet must have formed extremely far away from the sun. Otherwise, it would have lost its CO and N2 long ago. And also along that vein, note that R2 PANSTARRS has a 20,000-year orbit, which means this is not its first passage into the inner solar system. This is not direct from the Oort cloud. So it has had a few passages within the planetary region before, and that has not managed to deplete these incredibly volatile species such as CO, N2, and CO2. So then also talking about the possible, just as far as the atomic abundances. So if you assume that we are seeing that the CO and CO2 are the dominant volatile reservoirs for carbon in this comet, and that N2 is the dominant volatile reservoir for the nitrogen, then the carbon to nitrogen ratio is about 10 in this particular comet, which is twice the solar value, but lower than typically seen in comets, which is about 20. Also, I'll note in typical comets, ammonia is the dominant nitrogen carrier, not molecular nitrogen. And also to note that CO and CO2 are also the dominant volatile reservoirs for oxygen in this particular comet, not water. Though, of course, the recent detection by Rosetta of molecular oxygen always leaves open the fact that there could be a lot of molecular oxygen in this comet. We can't quantify that at this time. So what this could mean is that R2 PANSTARRS could have formed in an area where carbon over oxygen ratio was greater than 1, allowing most of the oxygen to be locked up in CO and CO2 and not really leaving any oxygen left for water. However, a big caveat here is this is just talking about the volatile composition. We have no idea what the dust composition in this particular comet is, and therefore we don't know, carbon-oxygen ratios in the dust. That could be very different from what we're seeing in the volatile phase. All right, so this is our preliminary work. We have lots of other observations at all different wavelengths. We still need to kind of finalize our analysis of the Spectra imaging and our iShell CO observations. It's been actually very hard to get a really robust measure of the water production in this comet. The water production I used for this talk is based on observations of atomic oxygen, which is subject to interpretation, and also especially with all the CO and CO2 present, that complicates interpretation of that emission feature. And so we're hoping to have a paper out on this in the next couple months or so, and I would just stress to stay tuned for that. And with that, I'll take questions. Thank you.
Do you have any questions for this talk? For Adam? So, have you gotten UV observations already? So basically the observing season for this comet has pretty much come to a close. Dennis Bodowitz was able to obtain observations with the SWIFT satellite, and that is particularly powerful for studying OH, which can be used as a proxy for water. So that's what really we're hoping from those observations. So that's the kind of the UV observations that I know of at the present time. Oh, we have a question in the chat box. Is someone, from Jeff, is someone observing at thermal IR to estimate the total dust amount?
Not that I know of. I guess that's the short answer. Maybe somebody is, maybe someone like Diane might know, somebody who specializes more in dust observations and comets might be more akin to what observations are planned or were planned.
It has very little dust, am I right?
Yeah, from the, definitely from the, so actually I can, so from that Spitzer imaging, it does look like there is very little dust. And you can also look, so here's the raw shellogram from the iShell observations. And you can see the very strong CO lines. I got them all labeled here. But basically there's no sign of continuum. So it does seem like the gas-to-dust ratio is quite high in this comet.
What we certainly can say is that there's very little thermal emission from dust. I mean, because this is at 4.7 microns where the CO is, and yet there's no continuum at all we could see anywhere really, L or M band.
We have a comment from Diane saying maybe someone from the southern hemisphere. She says it's too faint for Sophia and IRTF. What about Subaru Comics?
Yeah, I don't know. Yeah, I mean, again, like we've been definitely focusing on the gas component and trying to quantify as many volatiles as possible in this comet. Yeah, so we're hoping some people have done complementary dust, but I'm not aware of any observations that have been done.
Okay. I think we better go to the next talk. Thank you very much, Adam.